Welcome to another video of Stat 420. We're going to continue reviewing the t-test, and in this video we're going to focus on the two-sample t-test. So a two-sample mean comparison has a lot of similarities, but there's going to be some differences in the math that we should briefly talk about. So first let's look at an example just to kind of set the context here. Let's say that we're comparing the means of two different populations or distributions. We want to know if maybe the means are equal, maybe the means are different by a very particular amount, which we'll talk about in just a second. But the idea is I have two samples from two different places, and I want to know if the populations they're coming from might have the same mean, or in essence might just be the same. They're really just coming from the same population, even though I'm getting them from two different places. So here our question revolves around the average age of patients in the ICU with the flu versus patients in the ICU with COVID. So we're going to start with our samples. We're going to assume these are random samples of people, which is a lot easier said than done. This is not a sampling class, or a survey class, which means there's a lot of details that we kind of skirt over when we say this. But let's just assume these are random samples and we can trust that. So we have these results. Our X bar and Y bar, I'm going to call them X bar and Y bar in this example, is 80 and 72. By the way, we could call them X bar 1 and X bar 2. We could call them anything we want, but we'll do X and Y here. So obviously there is a difference in the means in my two samples, but they're also pretty small samples. So it seems like maybe this could just be random chance, that if I collected more data from each of these populations, that maybe the sample means would begin to converge. So this is a good thing for us to test. Is this enough of a discrepancy to give evidence of a difference, or is it still kind of in that sampling variability range that they could have the same means, it turns out? Well, first off, the central limit theorem still applies here. And that's because the sampling distribution we're interested in is the sampling distribution of X bar minus Y bar, that if I repeatedly take samples from these two populations and subtract one sample mean from the other, and then plot that difference, my sampling distribution is a distribution of mean differences. And this too is probably going to be normally distributed if my two distributions meet the criteria from before, that either X and Y are already relatively normally distributed distributions as they are, or that I have sufficiently large sample sizes from each one such that the distribution of X bar and Y bar should at least be normally distributed. So if I can make that assumption, then I can assume the distribution of X bar minus Y bar is normally distributed. So for example, my sample result is 80 minus 72, and that's going to be 8. But let's say that I take another random sample from each distribution and I get 77 minus 73, that's going to be 4. Maybe I do it again and I get 74 minus 81, and that's going to be negative 7, right? So if I keep sampling and taking the difference of my sample means, I am creating a distribution of possible sample mean differences. So I have an 8, I have a 4, I have a negative 7, right? And so if I keep doing this, I would keep kind of building up this distribution of possible sample mean differences. And according to the central limit theorem, there's a very good chance this distribution is going to be normally distributed if one of those two assumptions is true, that the two distributions are already pretty normal, or that I have sufficiently large sample sizes such that X bar and Y bar would have normally distributed distributions. All right. So if we can run ahead with that assumption, then we can again use a t-test to help us make this comparison. But there is one more kind of decision that we have to make, and that's if we want to do a pooled method or an unpooled method. So now that we have two different groups, we have to decide if we want to assume that the two distributions have the same variance, or they might have different variances. And there's different things that we could do to make that decision, but the idea is if we want to assume the variances of each group are about the same, then we could use a pooled method. in which case we kind of create a singular pooled standard deviation. So that's what this is doing right here, is we are calculating a kind of a singular pooled standard deviation to represent both distributions by pulling our information together, weighting it by sample size, so the one with the larger sample size gets a little bit more weight in this calculation, and then following through. And then we would have a standard error for x bar minus y bar, plugging this value into the formula. If we want to run ahead with an unpooled method, then that's also okay. We would just calculate the standard error with this calculation. In general, though, the unpooled method is going to be a slightly weaker test, meaning that it's not as easy to correctly reject the null hypothesis in an unpooled method, that we would need a larger sample to have the same power as a pooled method. So that's why it's nice to make that assumption when we can. But again, if we can't make the assumption, if we don't have good reason to, then we should just do an unpooled method at that point. All right, so let's go ahead and assume a pooled method and run through with that. So let's pretend that we've calculated the pooled standard deviation, we've plugged it into the formula, we plugged in our information, and we get a test statistic of 1.823. One observation I want to make here, and that is with this mu sub naught. If our null hypothesis is that mu sub x equals mu sub y, then mu sub naught equals 0. So in other words, if we're assuming the null is that the two means are the same, then there is no constant added to the numerator, right? It's just going to be x bar minus y bar as part of our test statistic calculation. If the null is that there is some constant difference between mu sub x and mu sub y, so I'm going to say mu sub x equals mu sub y plus some constant mu sub naught. Or actually, I should say, let me do this. I'm going to say mu sub x or mu sub y plus constant, then mu sub 0 equals that constant. So honestly, that's not a very common test to do. Or I guess what I mean to say is that in my experience, I rarely see the need for a constant difference test. Like most of the time in realistic situations, you're testing the first of those things where the constant difference is 0, that you're testing if the two means are the same. But you could do this constant difference test if you wanted to. Okay, so we have a test statistic of 1.823 if we plug in our information from each. By the way, n is going to equal 6 in this case, or is it m equals? I think that's I don't remember what order it was anymore, but I think it was this. We calculate the pooled standard deviation from this calculation from earlier, and then we have our x bar minus y bar is going to be 80 minus 72, I believe, if that's the order there. Okay, so we could again use the PT function here to find a p-value. We plug in our t-value. Our degrees of freedom in this case is going to be 12. And in this case, if we're doing a one-sided test in our lower tail, we would say lower tail equals false because our test statistic is going to be on the positive side here, right? So we got 1.823. And the PT function always assumes you're looking for a lower tail if you don't say otherwise. So that's why we need that addition there, is if we're looking for this right over here, we would need that lower tail equals false. Otherwise, we're going to get all of this. Oop, I'll get that deleted there. Okay. And put my t distribution back together. Okay. And so we get about 4.67% for our p-value here. Now, if we wanted to do a two-sided test, we could just multiply this value by 2, right? So we could just take what we got times 2, and then we would get a two-sided p-value there if we wanted to. I don't think the question was super specific what we were looking for. We were just looking for a difference in age. So that makes me think that maybe a two-sided test makes a lot of sense. So I'll go ahead and add that in here as kind of the default here without more information, is that I would think a two-sided test makes sense here. So I'll do, keep messing this up. 4.67%. So then my p-value here is going to be about 9.33%. All right, so again, we do have a t-test code that we can plug in that's going to be a little bit simpler. So there's going to be 4 arguments, there's going to be 2 variations of this, but the first one has 4 arguments. The first is your first data vector. The second is your second data vector. The third is your alternative direction. And the fourth is your equal variance option. If you want to do equal variance, a pooled method, or if you don't want to do that, if you want to do an unpooled method, you could say false there as well. And this would be pooled. We get this t-test result. Apparently, this is a this particular t-test assumed that we were doing a one-sided test, where alternative is that it is greater. Again, we have the option of doing a 2-sided test as well, and we would get double that p-value if we chose to do that. Okay, so here we get the same p-value that we just saw, 4.66 around there. It produces the t-value, degrees of freedom, as well as our mean values. We could also, again, get a confidence interval with the 2-sided test for the true mean difference, but a one-sided test is going to give us something kind of wonky there. Now, if your data is already in a data frame, so let's just say that I don't have 2 vectors, this is another common setup here for the t-test code, and that is to identify your numeric variable, tilde, your grouping variable. So whichever variable your values are in would go first, tilde, and then your group name variable would go second. Then name your data set. So this, in this case, would be, if we called it t-test data, which is apparently what it's called here, then that is what you'd actually plug in there for that next argument. And then again, your alternative direction and equal variance option would be the same there. So we could run it in that format as well. This is what it would look like. We again get the same result because it's the same test, just a slightly different way to enter it if your data is in a data frame and you just want to enter it like that.